The objective of this lab was to show an object falling with constant motion and to demonstrate how we can also use Newton's second law to make model predictions of the same object falling with constant motion. Before we get into the experiment, there are a few basic concepts we will want to address. First, what is Newton's second law? Newton's second law states that for an object that is accelerating, its acceleration is proportional to the magnitude of the net force it experiences and inversely proportional to its mass. From this definition of Newton's second law, we can use the definition of acceleration to rewrite our definition. We know that the acceleration of an object is equal to its change in velocity over time, delta t. We can rewrite the equation to show how changes in velocity are directly proportional to the net force exerted on an object over time. For this lab, I recorded a falling object in motion. I recorded myself dropping a soccer ball from a height of approximately 1.5 meters for 0.4 seconds. I then uploaded my video observation into Tracker to derive the position of the ball during 12 frames. In order to establish a frame of reference, I used a calibration stick that measured the diameter of the soccer ball to be 0.27 meters and adjusted my right-handed axis to a tilt of negative 1.8 degrees. The data of the object's y component disposition over time was plotted in on a displacement versus time graph. With an initial velocity of 0, the curve produced from the data suggests the object did not experience constant velocity throughout all 0.4 seconds. This can be due to a non-zero net force acting on the object. I then created a model in idle to predict the motion of my falling soccer ball. I included initial conditions about the mass, position, and velocity of the object as taken from my tracker observations. I also included a non-zero net force acting on the object, which I assumed only to be force of gravity from the Earth. The graph shows a model prediction of the ball's displacement over time compared to the observed displacement versus time. Our model shows a pretty good match of the actual observed displacement of the ball, but what could make the model fit better? From looking at our actual and computational model prediction, there's a noticeable deviation of the two lines after 0.2 seconds. At this moment in time, our computational model suggests that the object falls more quickly than our actual observations show. Initially, I assumed that the only component of the force acting on the object was gravity, but for objects with large surface areas or objects falling at high speed, air-resistant forces or air drag will act on the object as it travels through the air. To accommodate for this difference, I added in the drag force as a component of the forces acting on the object. Adding in a drag force shows how we can better predict the motion of a falling object. We cannot always assume the forces that are acting on an object along the y-axis are those we can see in gravity. In this experiment, accounting for a drag helps better predict the change in the position of the object until 0.3 seconds. Our first model excludes the drag force, but better supports the falling soccer ball on some components of the graph. We can make notice of the point deviations that don't seem to follow a trend in both models and consider the role that human error plays in using computer software. In my initial experiment, the ball was dropped with an initial velocity of 0. But we can consider what would have happened had I forcefully thrown the ball down. The ball would have taken on a non-zero initial velocity because force was acting on the ball as the ball was released from my hands. For this lab, I demonstrated the effects of a non-zero initial velocity, which I set to be negative 0.4 in the y direction in our computational model. I then plotted the results for comparison to our computational model with an initial velocity of 0. From the first point on the graph, we can see that the two lines deviate from each other, suggesting that their velocities differ. This is also evident in the increased terminal velocity of the model that begins with a non-zero initial velocity. If you remember back to the beginning of the presentation, I talked about the relationship between the velocity, time, and acceleration. I also mentioned that acceleration of an object is directly proportional to the net forces acting on an object. This explains the linear relationship of the change in velocity of the object when it experiences both a drag force and no drag force. Although the lines do not match up perfectly, they both display a constant change in velocity over time with respect to the net forces acting on the object, or a constant acceleration.